Okay, let's now think about some implementation details in MATLAB, and this is particularly thinking in terms of the Q-Learning laboratory practical that you'll be doing. So we have to think about things in terms of episodes, trial and experiments. So as we've said, an episode then is when you start somewhere and you take multiple steps and you finally get to a terminal goal state. Right? And generally that starts from a random state, and obviously the goal state is generally fixed. A trial then consists of multiple episodes, and you need a trial because with multiple episodes in it to actually learn the Q values effectively. You would generally stop doing the trial or stop doing another episode when you've got a fairly good convergence on the Q values that you're actually looking for. And we'll generally also, over the episodes and over the trials, we're using each of the steps in each of the episodes to update the Qtable, and we do that using the update, which is effectively a running average. An experiment, the way we're defining it, consists of doing multiple trials, and the reason we want to do that is because we want to see what's typical of the performance of this algorithm, and we can't just rely on just doing one trial, because we could have been unlucky and got a really bad result, or we could have been really lucky and got a very good result. We want to know in general, on average, how is this kind of task performing, and also look at the variance between different trials. The important thing to do when you're running experiments then is to make sure you always start off with a random Qtable, because it needs to update basically from a random start across particular trials. Within a trial, of course, you've set up the Qtable once, and then it's learning across the multiple episodes. Like I said, if we do an experiment, we'll end up with measures coming out from each particular trial, and we can calculate the mean and standard deviation. So looking at what performance, let's say we're looking at a particular episode, one way of getting an idea how well it's working is to see how many steps it actually takes to actually get to the end, right? So how long does it, how many steps does this thing in a maze, say, take from a starting position to get to the ending position? And as it learns the Qtable, it'll need less and less steps, of course, because it can then find the best path through. So as the number of episodes goes up, right, it should be learning more and more and more. So the number of steps it takes should come down as the number of episodes goes up. So this is for one particular trial, and we can see this is fairly noisy. And if you ran it again, you'd get a slightly different result, because a lot of this is randomized due to different random starting points and starting values. So the idea then of the experiment is we get lots of these trials, and we average across them, and then we calculate error bars, and that's what this lower plot will show. It's showing then the mean, if you like, number of steps against episode number across a lot of different trials. And of course, because we've got a large number of trials, or quite a few trials, we can also look at the variance across them as well, or plot the standard deviation. So you'll be doing some practical work on the McCallum maze, because it's quite a nice little grid world, and the idea will be, from any given starting position, you want to get to the goal state, right? And you'll need to implement Q-Learning in order to find optimal policy that will move you to the goal state from any starting position. Pseudocode, well, we've been through that already, but basically, yes, you need to follow the pseudocode and implement the pseudocode in order to do this. So you'll need a function. First of all, you need to loop over multiple trials, and then in a given trial, that's what the pseudocode from Sutton and Bartow actually shows you. And what we see is you'll loop over each episode, and within each episode you'll loop over the trials. In order to actually get this to work, what you are first basically is to start with, you've got to actually model the environment. So you'll need to build a transition function, and as we see, we've got actions. There's 4 possible actions that you can take on a maze: north, east, south and west. You probably want to number them 1, 2, 3, 4. I use the same ones as I'm using here. The states on the maze are given here: 1, 4, 7, 8, 9, 5, 2, 10, 11, 6, 3. And what you'll first of all need to do is to build a deterministic, in this case, transition function, so that if you given a certain action, where do you end up? So let's say I started in state 1 and I moved north, right? So I tried to move north, I'd end up in state 4. So the transition function would be, given state 1 and given I take action 1, I'd end up going to state 4, and so on for all of them. So you have to write up that table. So this is the kind of thing that you might want to set up. You build a transition function which takes a state, right, the state you're in and the action you're going to perform, and then it's going to return the state you end up in. And like I said, this is a deterministic question in this particular instance. So we've defined here actions, so you can actually write them down as north, east, south, west, so you don't have to remember 1, 2, 3, 4. And the way that this would work would be, as a single example, imagine you start in state 1, right, and we move east, right? So if we move east, right, actually you hit the edge. So what we say is, if you move out of a state and there's nothing there, then you stay put. So what we say is, if you're in state 1 and you move east, you stay in state 1. If you're in state 1 and you move south, that goes off the maze again. So we say you stay put again. So grid world state transition matrix for 1, state 1 moving south again gets you back to where you were back in state 1. And the same thing for west, you'd move off the grid if you moved west. So grid world 1 for action west stays put with 1. But in this case, if you're in state 1 and you move north, right, you end up in state 4. So grid world 1, north equals 4. I'm just calling it grid world. You could just call it transition matrix or whatever you want to call it. And then, this is just, if you like, initializing the transition function here. That's all I'm doing here. And you just, in the way I've done it here, I'm just building it each time in this function. Then when you give a given state and action, all you need to do is look up this transition from the matrix that you've just built. So from an arbitrary state and an arbitrary action, you just choose the element state action, which gives you the next state, and that will be your transition function. So there's state 1. So you're going to have a function which generates random starting states, and that can be anywhere on the maze, except we don't want to start at the end, right? So that's just quite simple to do. Build a starting state and generate randomly one of the allowed states other than 2. We need to generate a reward function that takes a state and an action and returns 10, let's say, if the state is 5 and the action is 3. So, in other words, if we're in this state and we move south, then we have a reward, otherwise we don't, right? Otherwise, in all other cases, it gives a 0. So, build a reward function, you give it the state and the action, and it'll tell you what the reward is. So you have to decode and put appropriate things in there. Q function table. So in this particular instance, a Qtable is going to be a Qtable of the states, and for each state, all the actions you can take for it. So clearly, in this case, we've got 11 states, and each state has got 4 actions, like north, south, east, and west. Therefore, it's going to be an 11 by 4 matrix. And to start with, let's randomly set it to some values, in this case between 0.01 and 0.1. So you can use your knowledge of using, let's say, uniform distributions and setting the minimum and maxima in order to do that. Then plot it just to see, just to get a feeling for what kind of values you're actually getting. So we know how to sample from a uniform distribution, like I said. Work out the range you want, work out the mean you want, and then basically get your random uniform value between 0 and 1, take away 0.5 to make it symmetric about 0, scale it by the range you want, add on the mean, and that will give you the value that you want. So in terms of the upper and the lower values, it's quite easy to calculate your necessary values for the random values for the Qtable, right? Function table. So we need to initialize then the Q values. That's quite easy to do. You can write a little function that does all of that and plots everything out. Action selection, right? You want to write an epsilon greedy function now. So what that's going to do, it's going to look at the Qtable, and so let's say epsilon is 0.1. That means 10% of the time it's random, and 1 minus 0.1, which is 90% of the time, it means it's going to pick the action with the largest Q value. So it's easy to make that kind of decision, but you'll need to write a function. You give it the table, the Q table that you'll have built. You'll give it the state, and then it'll do an epsilon greedy selection, right? The update function, again, is quite easy to do. All you have to do is make sure you use the right values for temporal discount and right values for the learning rate. And in this particular case, it's something of this form. Your update function, you give it the Q value, you give it the state and the action, and the resulting state S prime, give it the reward, give it the alpha, which is the learning rate, you give it the gamma, and you give it here also an exploration rate. And it's basically this line that this has got to actually implement this, your update, your update for Q, S and A, right? That's what we need to update. Now to build an episode, what we need to do then is we need to start off with a random starting state. And it should just run a number of loops. So that's going to be, the episode is going to be this loop here, right, running over. So it's effectively just a for loop to run, or a while loop just to run all the steps until you end up getting to the end point, until you reach the goal. And that could look something like this. You're going to pass it the Q values, alpha, gamma, exploration rate, and tell it when it's finished. It needs to know where it's terminated, and it's going to return the Q table and the number of steps it took to get to the end of the episode. And in effect, it can be run just using a while loop. Is it running? It's running until it gets to the end point. And I've just put here just some very simple pseudocode. In goes your code. It's going to have to make a greedy action selection, get the next state, get the reward, update the Q table, look if it's got to termination, update the states, and update the number of steps. A trial then is just going to run across multiple episodes. I mean, you might want to do more than 100 on some slightly bigger mazes, but the idea is that you run lots of episodes so you can actually do quite a good job of learning the Q values. You only need to initialize the Q table once in a trial, right? And then you run your loads of episodes, and across the episodes it's always continue updating the same Q table. And you should also return the steps for each episode as well, so you can actually plot them out. Okay, so we do need to make sure we plot out the steps, so you can start to see whether or not it's actually learning as we go through the trial. And that's again something fairly simple to do. I've just written some example functions for you here's the one for trial. You give it the alpha, the gamma, the number of episodes you want it to run, expiration rate, and it's going to return for a particular trial this array of steps. And the point being, in a trial, it runs over a certain number of episodes, and for each episode, you're using your episode QLearning function there. And an experiment, again, is just running over lots of trials so that you can compute the mean and standard deviation of the steps. Okay.